Morning, good afternoon, and good evening to everybody who is listening to me. I hope there are no issues with the sound. It's my great pleasure to introduce Li-Cheng Tsai, our speaker today, who won the Bernoulli Society New Research Award in Probability for his excellent work in what I would call statistical physics. And despite the fact that it's a new research award, the work Li-Cheng has done in last years is extremely impressive. So he published several papers in PTRF and also probability, communications in mathematical physics and so forth. And it's really a great pleasure to welcome you here and to listen to your wonderful talk on your recent result in KPZ equations. So you're very welcome. The floor is yours, and we're looking forward to your talk.
Thank you so much. Should I take it over?
Yes, please.
All right, thank you so much for the very nice introduction. Thanks the Society for this honor. Thanks to the Society for putting together this wonderful event, and thank you all for coming. All right, so today I'm going to talk about some result and properties about some specific examples of stochastic PDEs. All right, so actually let me just jump right into the equation that we'll be working with are the one on the left, KPZ equation, and the one on the right, stochastic heat equation. All right, so let me start from the one on the left. It's named after the three physicists called Parisi and Zhang, who introduced this equation in the mid-80s in the context of random surface growth. So what they have in mind is the equation that models a type of random growing surface. And what you're seeing here on the left is sort of a schematic drawing of kind of physical phenomena. There's an interface that is dynamical, that is growing in time. So t is the time variable here. And x is the space variable. And for most part of the talk, I'm going to focus in one space dimension. So x is in R for most part of the talk, though I'll jump into 2 dimension later toward the end. Now, underlying this entire surface growth phenomena is an ambient driving force, which is given by this C here. So this is the space-time white noise. So formally, that's a Gaussian process with covariant function being delta. But the way to think about it is just some kind of Gaussian ambient force that is uncorrelated across different points in space and time. And one way to think about it is imagine that snow is being fallen from the sky. Or if you are in a lab trying to grow a membranes, these can be thought of as the gaseous molecule that's being bombarded onto a given substrate. So these are ambient forces that drive the whole thing to grow. Now, on top of that, the surface has 2 kinds of physical mechanisms, intrinsic mechanism that it can respond to this external ambient force. One is given by this Laplacian terms here, which is a local smoothing effect. It says that locally, the surface has a tendency to smooth it out a little bit. And then there's this other term, which I'm going to call it as the slope dependence growth. It says that locally, the speed of growth around that place is a function of the local average slope, gradient of h in x. Now, what you're seeing here is a specific function of the gradient, the quadratic function. Why is that so? Well, physicists have this heuristic. It says that if you give me a generic function of the slope, if the speed somehow depends on slope for a generic function f, I'm going to just Taylor expand. Okay, so here comes a constant, here comes a linear term, and here comes a quadratic term, and so on and so forth. Now, for the constant term, I can easily remove it by just having an overall change in growth velocity. So I can kill this constant just by introducing a shift. As for the linear term, I can just change my observation coordinate. I'm introducing velocity to my coordinate frame. I can kill the linear term. And hence the quadratic term is the first non-trivial slope dependence. And these three physicists propose it as sort of a paradigm or a toy model for this kind of growth phenomenon. All right, so that's the story about KPZ. Now on the other side, we have the stochastic heat equation. The first two terms of the equation is just a good old heat equation. And added to that is the space-time white noise that acts multiplicative. So this Kc is again the same space-time white noise that acts multiplicative on the last term. Now this equation, stochastic heat equation, comes up in a lot of places. Now I'll mostly focus on one physics phenomenon, which is directed polymer in a random environment. So what happens is that if you look at this equation, you can sort of pretend Kc is just an external potential. And we know how to write a solution of such kind of equation in PDE through the Feynman-Katz formula. So this is the result of Feynman-Katz formula, where the expectation is taken over a Brownian motion, this Bs, that goes back from xt, going backward in time. Now, such a thing can be reinterpreted as something that is shown here in this picture I'm putting in a box here. So what happens here is that you have a random environment given by this Kc, which is simulated, which is sort of represented by this noisy dot picture here. That's the environment, like being noisy. And in order to find a solution, you start out the place where you're looking at xt, and you send this Brownian motion that goes backward in time. And this Brownian motion pick up whatever it collects about the noise, and then raise it to exponential. That's this thing. And then at the end, you just pick up whatever initial data you have in the end, and you average over different realizations of the Brownian motion. So this system has interpretation of embedding a path, directed path is being called polymer here in a random environment. And formally, Z is the partition function of this model. All right, so on the two sides, we have KPZ and SHE, and they are good for their own separate physical phenomena. How are these two things related to each other? Well, history goes back to 1949. So if you look at the equation without the noise term, it was well known that the two sides of the equation is being connected by a simple transformation. Exponential h is equal to z. Okay, so this was observed by Hoff and Co. And this is just simple calculus. You exponentiate this function, you plug it into calculus, it tells you that this equation on the left transforms into heat equation on the right. It was proposed as a way to explicitly solve Berger's equation. Now, with the presence of the noise, if you ignore some issues about well-postedness, you formally do this calculation, it still carries over. If you just formally do this, KPZ formally transform into the stochastic heat equation. And this Hoff code has been elevated to that level. Now, there's one thing I should need to confess to you, that the KPZ equation itself is not very well defined. The reason is that the solution of KPZ is very rough, as has been indicated here. And we know exactly how rough it is, as rough as Brownian motion in space. It's heavier and half minus and not better. So this gradient of h here is at best a distribution that is fine, except that you're taking square of it, so it makes it very problematic. And there's a lot of effort that goes into equation of this types. And right now we have a regularity structure and parallel control distribution and so on, theory that can tackle the well-postedness of this kind of equation. However, for this special case, with the presence of Hoff code, there's another simpler alternative that we can use to define the KPZ equation, namely Hoff code. The equation on the right here, the stochastic heat equation, it doesn't have this quadratic nonlinear term. What you could do is you try to write a solution in what's called Duhamel form, and you start iterating the Duhamel equation. What you get out of it is a perturbative sort of series expansion, and just a matter of life that in one space dimension, this series expansion is converging in a very nice way. Put it differently, we have a standard way to define the solution of SHE on the right here, and we can simply call the solution to KPZ log of the SHE. So this is the notion of solution that goes under the name of Hoff code solution. Okay, and this is the notion of solution that we'll be working with. All right, so the focus of this talk is going to be about some very explicit long-time behavior of these random graphs, the KPZ equation, more specifically the tail probability, or formally the large deviation. And toward the later part of the talk, I'll try to convince you that information, this precise information about the tau can somehow be related or accessible from moments, knowledge about moment of the stochastic heat equation. So this connection between KPZ and SHE not only just offer a simple way to define the equation, it actually gives you a lot more leverage on the more quantitative detailed behaviors. All right. So let me do a little bit more specification. Okay, so throughout most part of the talk, I'm going to work on very specific initial data, though sometimes generalization will be introduced. The type of initial data I'm going to work with on the SHE side is just a delta at 0. I'm going to start a delta, the stochastic heat equation from delta function at the origin. Now, I told you earlier that the solution of KPZ is just log of SHE. That's all good, except that you can't take log of a delta function. So what does it mean for the initial data on the KPZ side? Now think about SHE, stochastic heat equation. When the time is very small, the noise wouldn't have wouldn't have played much of a role. So when time is very small, it looks as if you're just solving the ordinary heat equation. And we know how to solve that from delta initial data. The solution is exactly the heat kernel. So on the SHE side, when time is very small, the solution looks like just a heat kernel. And you take log of that, that's the notion of initial data on the KPZ side. If you work out the mass, you're gonna see that it's amount to something that looks like a very narrow parabola. Okay, being schematically shown here, I just drew it on the top left. Okay, so the kind of initial data looks like a very sharp wedge or parabola, and hence a narrow wedge. So we're gonna start our random growth from such initial data and just let it run. And the reason why I'm doing this is because there are some very nice explicit formula under such initial data. Okay, so I'm going to run it for a long time. I want to know the statistical behavior of the random growth if I look at this phenomenon. Okay, so here on the bottom right, the place where I'm circling is just a schematic showing of what the height function looks like after a long period of time. I'm going to pick up my favorite point, as always, x equal to 0. And ask myself, what is the statistical behavior of my random surface growth at that point? Okay, so when time is very large, parallel to this paradigm of classical probability, you can ask, is there a law of large number? Is there a fluctuation theory like parallel to central limit theory? Is there a theory about large deviation that parallel to Crimea theory? Now, the first two questions was answered around 2010. So in particular, this result of Amir, Cohen, and Questel, they explicitly characterize the centering of such height growth at later time. So there's this very explicit constant, t over 12. I'm doing 2t instead of t just so that the formula looks prettier. So what it says is that there's a very explicit characterization of the velocity of the growth, which is going downward by -1 over 24, something that we can somehow calculate very explicitly. And not only that, it says that the width, the fluctuation of the height grows like t to the 1/3. It's being written here. And if you scale back down by this t to 1/3 factor, you're going to converge to some explicit limiting distribution, which you think about this shape that's implied here on the bottom left. Okay, and that limit is the GUE trace-weighted distribution that comes out of the largest eigenvalue of a large GUE random matrix. So this is something that explicitly can be written as a Fredholm determinant or Panova equation. All right, so independently and simultaneously, this result was derived by 3 other physics groups around the same time, and has recently been extended to process level by Questel, Shakar, and Virac independently and differently. But this talk I'm going to focus in one point result. Okay, so we have, under our cover, law of large number and fluctuation. I saw there's a question. Should there be h minus, oh, actually it's plus. So the growth is a little bit counterintuitive. The height actually is going downward instead of upward. Yeah, it's growing downward actually. So the compensation is plus, you compensate by plus that amount to center it. Did I answer your question? Let's see, the nonlinearity has a plus sign. Okay, I see. Okay, I see. This is pretty subtle because the equation, the KPZ equation cannot be interpreted literally. There's this ultraviolet renormalization that goes in, right? So it looks a little bit counterintuitive that this nonlinear term is positive. You would think that growth is going up. But the truth is you can't interpret this nonlinear term literally. There's an ultraviolet renormalization that goes into it. So it's like this thing minus a gigantic constant, which is in fact infinite. And take into account that constant, the way growth is actually down. Now, another way to see why it should go down, if you go, for people who know the context, is you go to particle system. We know that asymmetric simple solution process converges to KPZ equation. Now, if you write out the equation for asymmetric simple solution process, you'll see that there's a negative constant that comes out here. And work out that constant, you'll see that the growth is actually going down. Yeah, so thank you. Yeah, that's actually, it's always a Panario point of confusion. All right, so I hope it's clear. We have the low flux number and fluctuation result about 1 point distribution, and the talk is going to be about the third part, tail or large deviations. So specifically, I'm going to look up and down by distance t, where t is time and going to infinity, of the typical value of the height, of the height. And by general wisdom in large deviations, we know that this kind of probability is typically exponentially small. And it's exponentially small in this t. Now, one thing that you notice from this picture here is that even though both upper and lower deviation are rare to happen, the rates are different. It's exponential minus t for the upper tail and exponential minus t squared for the lower tail. Namely, even though it's unlikely to see upper and lower deviations, it's much more unlikely to see lower than upper. And for those of you who are familiar with random matrix theories, it's not uncommon. You always see this kind of asymmetric behavior in a lot of these random matrix ensembles. Now, in the context of directed polymers, I'm offering you another qualitative explanation. Okay, so here it is. Now, this is a picture of this directed polymer, and this is Feynman-Katz formula again. Okay, so you ask yourself, what kind of deviation of the background noise could you cause the height or the partition function z to be much bigger than its typical value? Well, one way that could happen is you just have the noise being enormously large within a corridor around the origin. If that is the scenario, then those Brownian motion that hovers around the origin would already pick up those anomalies, right? And because the thing's been exponentiated, you're gonna feel such anomaly immediately. However, you wanna pull off the same stunt for lower tail deviation, this kind of trick won't work. Why? If you have something that is small on this corridor, it's gonna only affect those Brownian motion that hovers around the origin. Every other Brownian motion won't feel, and the whole thing is being exponentiated. So it's not gonna affect the whole thing that much. And in order to make the entire z to be much smaller than typical value, you see that you have to have the y noise to be much smaller than typical value on a large region. And that explains why lower deviation is much harder than upper deviation. Now, I'm not going to go into why exactly is t squared versus t. So moving on, the next thing that we are interested is the rate functions. Namely, instead of just the order of the probability, we want to know exactly the prefactor here, phi plus and phi minus, depending on how far away the deviation is. And in the theory of large deviation, that's rate function. We want to know what is the rate function. Now, one thing that you notice, because of the fluctuation result I told you earlier on the previous slides, right off the bat, we know some asymptotic behavior of the rate function. Namely, when alpha is very small, we expect that the rate function behaves the same way as the Tracy-Wheelan distribution. Now, it is known from random matrix theory that the Tracy-Wheelan distribution has this very explicit behavior, 1/12 alpha cube to the lower side and 4/3 alpha 3/2 to the upper side. So this is something you can calculate from random matrix theory. These are exact rate function of the Tracy-Wheelan distribution. And just because the thing has the same fluctuation as Tracy-Wheelan distribution, we expect the rate function to behave similarly as that thing there. So an analog of this is in the classical Crimea theory. Even though the rate function depends on, the entire rate function depends on the underlying random variable. Whatever random variable is, the rate function has to be quadratic near the minimum. And this is the analog of that in the context of Tracy-Wheeler distribution. All right, so physicists look at this problem pretty early on. So in particular, one of the physics group, which on the bottom right here, they predicted that this free-half law, it doesn't just hold near the origin. It actually extends all the way out. The entire upper tail they predicted is exactly the free-half law by analyzing an exact formula, which I'll get in a moment. On the other hand, for the lower end, another two physics groups, they predicted that there's a crossover behavior. When alpha is small, it's predicted to be this cubic law. And when alpha is very large, namely approaching very deep lower tail, it's predicted that you're going to have a 5-half law with this very explicit constant here. I'm not going to get into the detail of the method. It's a method that goes under the name of optimal fluctuation theory, which a priori only hold in short time, but for some not fully understood reason, it persists in long time. Okay. And in the next few slides, I'm going to tell you, a few recent results that prove this phenomenon. All right, so the first result is a joint work with Shai and Das, where we prove this prediction that the upper tail deviation is given exactly by this Tracy-Wheeler free-half law. And this result has been extended to general initial, so I'm working with narrow wedge initial condition, and this result has been extended to the general initial condition by Permin Gouchot and Yearling, extending to what's called half-space geometry by Yearling. All right. Now, one thing I should tell you first is that it is pretty standard theory that in order to get a large deviation, you could alternatively also look at just the log moment generating function. If I can get my hands on the asymptotic behavior of the log moment generating function, which is what written in the second line here, then by standard Legendre duality, I can go from one into the other. Okay, so in particular, the thing that's written on the second line for a standard Legendre transformation will produce the large deviation rate function, and that's exactly how we did it. We actually proved this result that's written on the second line, and then going from there back to the large to the upper tail rate function for Legendre transformation. Now, for the rest of the slide, I'm going to give you a hint or taste of how something like this could be proved. Okay, so one thing that lies behind a lot of this explicit, precise asymptotic behaviors of these SPDE are some exact formula that characterize the distribution of these stochastic PDEs. In particular, there's this elaborated formula that express some observables of the SHE or KPZ equation in terms of a explicit Fredholm determinant. Okay, so if you look at the quantity in the middle, that is the Laplace transform of a solution to SHE. It got expressed as an Fredholm determinant, where K here is this explicit integral operator, where AI is the area kernel. And you don't read too deep into it. We're not actually going to do calculation on the board. But the point is that it's entirely explicit. So it is plausible that you can try to do analysis from this explicit form. And this result, or an equivalent version of it, was derived in these 4 works that I showed you earlier about Tracy-Wheeler fluctuation. In fact, this is the backbone of that result. Okay, so here we have a characterization of the Laplace transform of the random variable we're interested in. And so by general probability theory, it tells us that there is a characterization of the probability law, right? It probably tells us that having Laplace transform is equivalent to characterizing the law. However, having a characterization in principle is different from being able to extract useful asymptotic information. So in particular, for this Tracy-Wheeler result I showed you earlier, what you need to do is to argue that somehow under that scaling, this operator here converges to what's called the area kernel. Now here I'm going to show you another example, how to extract the upper tail information from this formula. Okay, so the first thing is you remember the stochastic heat equation, Z is related to KPZ just through this simple Hofkow transformation, right? E exponential H is equal to Z. So the moment generating function here that I'm interested in is nothing but the piece moment of SHE. Now, had P been just integer, you would know how to proceed, right? We know how to extract moment from Laplace transform. You just differentiate this thing I'm putting in a box here in U several times, and then you set U equal to 0, that will give you moment. However, here P has to be all positive real number. So we need not just integer moment, but also fractional moment. There's actually extension to that, and probably not all of us know, but it's also pretty standard. So here's this formula here on the bottom of the page. So this is a generalization of that derivative tricks I just mentioned earlier. It allows you to extract the fractional moment, any positive moment, from a well-behaved positive random variable x. So what you need here is you take this nice explicit formula here, and you just plug it into this moment generation function, and that will allow you to develop explicit expression out of which you can do a lot of analysis. And then I'm not going to explain the rest of detail, but that's basically how we did. All right, so moving on to the lower tail result. Okay, so previously I told you that there's a crossover behavior between phi hat and cubic law. It turns out that we actually know what's the entire rate function here. So this is the thing I'm putting in a box now. It's this oddly specific, yet not too complicated rate function. So that is the exact rate function that's been schematically shown here. And you can do a simple Taylor expansion for alpha small and alpha large. You'll see that actually it does check this crossover behavior. Okay, and we as a community love this result, and so we derive it many times. So here shown on the screen, there are 6 not just independent, but 6 different derivations, 4 of which from physics, 1 of which I'm involved. There are, as of now, they are not completely rigorous, but they are valid derivations. And there are 2 proofs, one of you I'm showing you here, and this one that comes later. Okay. Now, also I want to mention to you another result which will become relevant later by Cohen and Gusho earlier in 2018, that provides detailed probability bounds of the lower tail of the lower deviation of KPZ, that in particular confirms this phi hat to cubic crossover behavior. All right, so for the rest of the slides, I again want to just give you a taste of how something like this is being proved. And the starting point is, as always, some explicit formula. That's always our handle in this kind of problem. And this is that formula I showed you earlier. This explicit observable of KPZ got expressed as a Freiholm determinant. Now, I didn't define to you what is a Freiholm determinant. Some of you might remember it, doesn't matter. But just take my word for that. The Freiholm determinant is by definition a series expansion. The 0th order term is just 1, and the 1st order term is negative of the trace of the operator. And the 2nd order term is some sort of quadratic trace of that operator, and cubic term is the cubic trace, some sort of cubic trace of that operator, and so on and so forth. So it's by definition a series. Now, what happens in the upper tail region is that this series behaves very nicely. It's been ordered. So the trace itself is exponentially smaller than 1, and the quadratic trace is exponentially smaller than the linear trace, and the cubic trace is exponentially smaller than the quadratic trace, and so on and so forth. So that's very good for analysis. For symptotic analysis, what you need to do is just pick out leading term and argue that the rest are subdominants. So what happened in the upper tail proof is that because I took derivative, so 1 is gone, so 1 is completely gone. And it turns out that the derivative of the trace is dominant. So you need to estimate the contribution of that term and argue that the rest are subdominants. However, for the lower tail, it's not, things is not as great. So there's no clear ordering between the terms. There's some back of envelope calculation you can do, and you'll find that the trace is actually much bigger than 1. There's no clear ordering between the terms. And it's expected there's some very delicate cancellation among these guys. And for purpose of analysis, this is something that's very hard to deal with. And what I'm showing you here is by no means a rare example. This kind of phenomenon prevails in modern probability, especially in random matrix theory. And in fact, there's a huge mechanism, should I say industry, that builds around such kind of problem. Among them is Riemann-Hilbert problem and other approaches. So what I'm showing you here is really one particular example of such a type where people manage to get away with it, to get around it. All right, so how do we deal with it? Well, most of the solution that I know use the following philosophy. It says that this Freiholm determinant expansion is not good, it's bad. So you try to look for another way to formulate the problem, try to convert the problem into something else, and with the hope that the other problem is more amenable for whatever purpose that you're looking for. So here's how we proceed in this particular example. So there's a result by Brody and Gore in 2016. They observed that this Fredholm determinant, through some trick about using some property of determinant, can be rewritten as expectation over a different stochastic systems. Okay. Now, there's a lot to unpack in this slide, so I'll try to walk with you slowly. Okay, so let me just first explain what is written here on the right. Okay, this whole thing here. It's expectation over some random point process on the real line. What is a point process is this lambda here. So it's a semi-infinite point process with the smallest one, lambda 1, lambda 2, and it's go all the way to infinity. So this is the random point process. And for those of you who are familiar with random matrices, this is the space reverse area point process. Namely, it is the scale limit of the lower end of the spectrum of the GUE random, of a large GUE random matrix. Now, for the purpose of the talk, I'm going to actually appeal to a different but equivalent definition of the area point process that is due to the work of Ramirez, Ryder, and Viren. Okay, so look at this random Schrodinger operator here. I'm putting in a box. This is an operator that's X on L2. You got the Laplacian term here. You got a potential X here. On top of that, there's this W, which W is a standard Brownian motion. So W prime is a spatial Y noise. So add to this operator a noisy potential, spatial Y noise. And it's not too hard to show that this operator is self-adjoint and has a fully discrete spectrum, and spectrum is bounded from below. So these lambdas are its eigenvalue. It's been shown that by these people that these eigenvalues has the same distribution as the area point process. Okay. And what you do is you then take these eigenvalues and you plug in this into this very explicit function f, and then you raise the exponential and you take expectation over these points. Okay. Now, for the purpose of this talk, you don't have to worry about what this f is. The only thing that's going to matter is it's the approximate linear function shown here. Up until a point, it's approximately zero sum. So it's approximately truncated linear, where this place of transition depends on both t and u. Okay. So this is a cartoon I like to sort of just mentally understand what's going on here. So what happens here is that you have these points that's being laid out nicely on a real line. And you have this cost function, this f function, which I think of it as a cost. And you plug in the eigenvalue to the cost function, you raise the exponential with a negative sign, you take expectation over this point process. Okay, so that's a lot to take. I hope it's not too overwhelming. So that, but the message is actually clear. So let's take one step back. What's happening? On the left-hand side is a stochastic system, the KPZ equation, the equation that we're interested in. On the right-hand side is an a priori disjoint stochastic system, the area point process of the stochastic area operator. However, through some algebraic work, it is possible to match explicitly some observable of the thing on the left to some observable of the thing on the right. And the hope is that I'm able to somehow convert the problem of interest, which is KPZ, into a problem of area, which presumably I have more leverage on. Okay. Still, it leaves open the question, how do I analyze the large deviation of the area point process? So in order to explain that, I'm going to appeal to an idea that is in this previously mentioned paper of Cohen and Gushin. So you ask yourself, how could this quantity here, how does this quantity here behave? Well, it's actually typically very small, exponentially small. But why is that the case? Well, the reason is simple, because this cost function is having a negative sign here. So you plug for those points that sit within the approximate support of this cost function, you're gonna pick up a huge negative cost. And you raise the exponential. Now I'm showing you a few points here, but in the scaling that we're considering, you should imagine there's actually a lot of points sitting in this approximate support of the cost function. So you pick up a lot of cost just by the way this function is being written. You ask yourself, is there a way for me to avoid the cost? Yes, there's a way. If I just push all these eigenvalues beyond the approximate support of the cost function, then I basically, because the function approximately zeroes out there, I don't pick up much of a cost. But you're going to be penalized because these eigenvalues don't like to be pushed. There's this notion in random matrix theory that says these eigenvalues tend to repel each other. So if I push these eigenvalues, it's going to be an unlikely event. It's going to be a rare event. And you can encode that in some sort of penalty. So on the left, I have a scenario where I have no penalty, but I have a lot of cost. And on the right, I have a scenario where I basically have no cost, but I have a lot of penalty. And using the knowledge of random matrix, it's not too hard to calculate contribution in each scenario. So on the left, you get this 5-half law by using random matrix theory. And on the right, you have this cubic law. Well, so among the results that's being shown in Cohen and Gouchon is that when you're probing a swallowtail, it's the right panel that dominates, that gives you this cubic law. And when you're probing a very deep tail, it's this 5-half law. It's the thing on the left that dominates and gives you this 5-half law. And with this in mind, you know what you should do in general, right? In general, you should just search for all possible kind of configurations or deviations and ask yourself, what is the one that optimizes both the cost and penalty? And the way that you go about doing it in this proof that I'm showing you is that you notice this stochastic heat equation is random in only one input, namely this Brownian motion. It's only random in this Brownian motion. So if somehow you can find a way to link this Brownian motion to the deviation that you're considering here, then you can probably find out what is the best deviation among all possibilities that jointly minimize the cost and penalty and proceed so on and so forth. So that's basically the idea of the proof. All right, I hope I have explained to you the underlying idea of this result about upper and lower tail large deviation of KPZ equation. And that got me through half of the talk, tails and moments. So I told you about tail, what about moment? Well, one thing that goes into moment is this explicit formula I've been using for the past 20 minutes. So you could think of what I've been talking about are just some application of this very nice formula. But I still beg the question, where does this explicit formula come from? Well, I'm going to show you a derivation which bears root in physics that goes under the name of replica approach. All right, so this is the observable that we're interested in. Well, so what we can do is you just Taylor expand the exponential and then swap the expectation with the sum, the usual trick. So what happens is that if I can get my hands some nice enough formula about the moment of SHE, I could try to sum up the series over M with good faith, with good hope, you know, that after enough work, I can manage to squeeze out of it a Frauenhofen determinant. But the big question is, how do I get explicit formula for the moment? Well, here comes an idea that I believe originated in the mid-80s. We are interested in the moment of this stochastic heat equation. Now you look at what's called joint mixed moment of the stochastic heat equation. You take n copies of the solution at the same time, different location. Take expectation. This thing is the deterministic function of time and n spatial variables. It turns out I solved the PDE. And the way you derive this PDE is very simple. You just use Ito calculus. In particular, this Laplacian term that you're seeing here comes just from the Laplacian term of the equation, stochastic heat equation. And this delta term here comes from the Ito correction term or contraction of the spatial white noise. So it's just, once you observe this is the thing to do, it's very simple standard Ito calculus. But not only is this a PDE, it's a linear PDE with this explicit linear self-adjoint operator. So linear algebra tells us, if I can get my hands on the entire spectrum and eigenvectors, spectrum decomposition of this linear operator, I could have a good control on the solution, which is the moment I'm after. And it turns out that delta Bose gas, this is PDE here, which goes under the physics name of delta Bose gas, falls into a category of quantum integrable system. So the upshot of all of this is that there exists a mechanism, a well-built mechanism that allows you to write explicit formula of the entire spectrum, an entire set of eigenvector explicit of this operator H here. And out of this explicit formula comes out a very nice multiple contour integral formula of the moment of stochastic heat equation. Now you take that very explicit contour integral formula, you take it back here with a lot of work, it's good faith, you sum it all, massage it, at the end you get to this Frauenhofen determinant here. Now that's the understatement. This is a huge undertaking in the past few decades. Now there's just one caveat I want to mention to you. about this approach. When I said this approach bears root in physics, I really meant it. So actually, there's some issue about convergence. So this moment here actually is not. It's growing very fast. It's growing like n cubic in exponential. Now, with that in place, this n factorial actually not going to make this thing summable. So actually, this series is divergent. This you can get from the first result I told you earlier, or actually has been proved directly by Kowen and Gusho, and also Li-Cheng. However, there exists some algebraic way to remedize this situation, and specifically the work of Bourdin, Kowen, and Sasamoto made rigorous of this approach. And there has been other approaches that derive this formula, which I'm not going to get into. Okay, so I hope I've explained to you that having a good handle on the moments of the SHE actually can be beneficial toward other purposes for example, quantitative precise information about the KP's equation. Now, this is all about one spatial dimension, but our curiosity doesn't stop there, right? So the last topic of this talk is going to be about the stochastic heat equation, but in two space dimensions. Now, first thing that comes to mind is that exact solvability is unlike in 2D. So of course, there's no proof that this is not the case, but generally the kind of exact solvability that we saw in the previous case is one dimension in nature. And actually, as a matter of fact, the stochastic heat equation, if you just write down it naively, it's actually not even well posed. If you try to do the same thing in one space dimension, you write this in what's called Duhamel form and iterate. What I realize is that each term within the series have a divergent second moment, and that's not allowed by the theory of Wiener chaos. The equation is not well posed the way it's written. Well, the standard way to come around this problem is, of course, you take a modifier, a compactly supported C-infinity function, and scaled by radius epsilon, and you just use it to smear out your noise, to make it smooth in space. And then you gradually take away this smearing. You take epsilon back to 0 to see what you get. However, in order to see a meaningful limit, you have to tone down the size of the noise, right? Otherwise, you're just back to where you started. So it turns out that the right way to tone down the noise is this log scaling that I'm showing you here. What's more interesting is that you don't not only have to do this log scaling, you have to put a constant, square root of 2 pi to be precise, oddly precise again, in order to see a meaningful non-Gaussian limit. So it has been proven by Caravena, Sun, and Zagreus that if the constant is too small, then you get some interesting limiting transition. There's some sort of ultraviolet renormalization, but the limit itself is Gaussian. The noise in that case is not strong enough to support a non-Gaussian limit. And there's some common belief that when the constant is bigger than 2 pi, you don't get a sensible limit. The thing is just complete banana. So you have to be not just have, we're in a situation where we not only have critical dimension, but also critical scale. So the natural question is now, can you characterize the limiting process as f1 goes to 0 of this object here? And as far as I know, it's still open challenge. And just to give you some background where the things sit, the theory, the recently developed theory of stochastic PDE apply to what's called the subcritical region. So in plain words, if you compare the strengths of this Laplacian and the noise at small scale, subcritical region is the place where this Laplacian dominates over the noise. And this equation at 2 dimensions is exactly the dimension where these two terms just compete on the same footing with each other. And that's the critical region, and most of these theories just don't apply. And this is also the ultimate reason why you're seeing this log scaling here. And just to put things more dramatic, it is conjecture, to some extent can be proved, but not really, that the limiting process here is independent of this noise that you put in. So you take an equation, you smear out it by f1. As f1 goes to 0, the limiting process is conjecturally independent of the noise that you started with. All right, so that's still an open problem. So that's just scale back down. If we can get a limiting process, it's something else that we can say about. One particular moment, right? I've tried to convince you that moment is something that can give you useful information in the previous part of the talk. And for second moment, by utilizing some radial symmetry, it is possible to get explicit formula of the second moment. And this kind of trick doesn't work beyond second moment, and the problem becomes very intricate. So the work of Caravena, Sun, and Zagreus, they utilized something I didn't mention, the chaos expansion to manage to find a limiting transition and expression of the third moment. But the problem becomes more and more intricate as you scale up, fourth, fifth, and sixth moments. So the last result I want to show to you is that as joint work with Hugo and Jeremy Questel, we found a unified way to obtain the limit of nth moment and characterize the moment. All right, so you start the SHU from generic L2 initial data, and you test it against a generic test function. Look at nth moment. And we show that as F1 goes to 0, this thing converges to an explicit formula of that is encoded in some sort of Feynman diagram. Okay, so I'm reluctant to write down explicit formula here because if I do, it would fit the entire page. But yeah, it's somewhat explicit. It's something that's being characterized in terms of Feynman diagrams. So how do we do this? Well, our work is largely motivated by previous work of Rajiv and Rajiv. So they say that instead of looking at stochastic heat equation, I'm going to look at delta Bose gas. And the connection to stochastic heat equation and delta Bose gas goes the same way as in one space dimension. So say if I look at delta Bose gas, and these people, they sort of consider delta Bose gas as some sort of toy model of quantum field theory, which I'm not able to explain in this talk. But they view this as a problem in some sort of critical toy version of critical quantum field theory and try to analyze it. So the upshot coming out of their analysis is that instead of looking at the moment in a time domain, t, they look at the Laplace transform of that quantity, which in analysis term is just a resolvent. So z is the Laplace dual of t. Look at this quantity. It turns out this guy is much more controlled, much easier to work with. And not only can they derive explicit formula of that, it can show the convergence of such a resolvent formula, which R star is some explicit limiting operator in L2. So we took their approach and show convergence of the resolvent in the context that we're working with. And a general theory of functional analysis tells you that once you've done that in good enough sense, you automatically guarantee the convergence of moment. Not only that, the limiting formula itself is the inverse Laplace transform of the limiting resolvent. So that allows you to bypass a lot of this very intricate analysis that would potentially happen in the time domain. You just go to the other domain, the Laplace domain, having everything done there, and inverse Laplace transform when you've taken the limit. Okay, so I've hit the end of the talk. So let me just briefly summarize it. The explicit formula that comes out of moments are good tools, very, very powerful tool, allow us to access detailed properties of the Kippe's equation, in particular the tail probability. I've been focusing on the long time region here, but the other region of interest could potentially remains to be investigated. Now, there's one particular phenomenon that we kind of observe in these studies. So large deviation itself is model dependent. It's not universal. If I, the rate function I show you is holding true for Kippe's equation, but if I do another model, it would be, or just a different region, I'll get a different rate function. However, there seem to be some universal behaviors that sit behind all these large deviations. In particular, this phi-hat law that I told you earlier, it exists in short time region and perceived through long time. So there's no obvious reason why that is true. And so there's probably some universal behavior that is sitting behind the scene that remains to be investigated. Now, venturing into 2D, there's much less known about in 2D. There's no exact solvability as far as I know. Still, there are some approaches that allow you to get information on the moments. And this approach of resolvent by Rajiv and Rajiv actually already opened up the door of some very interesting studies. So this explicit formula of a resolvent I did not show you. It is nice in itself. In particular, Rajiv used that formula to do some heuristic calculation. And he predicted the nth moment growth nth moment is growing like in 2 dimensions. And then there's this question of characterizing the limiting distribution of these 2D equation, which is still an open challenge. All right, so I'll stop here. Thank you for your attention.
Yeah, thank you very much for your presentation. It was wonderful. Maybe we can shortly unmute the speakers to give a clap. Will that work? Yeah, thank you very much. Yeah, it was a wonderful talk. It's now it's time for questions. Yeah. Are there? So let me check. Is it just me, or I don't see any questions at the moment? But maybe they'll come. Yeah. Let me start then with some of the questions. I mean, first of all, it was a wonderful talk. It's not a trivial topic, obviously, and you gave a very nice overview, and especially about the ideas. So my question is actually about the connection to random matrices. I mean, once we have seen the expression for Laplace transform depending on threshold determinant with array functions entering and so forth, it was somehow clear that we end up with Tracy-Widom distribution at the end. But is there, besides the mathematical computation, is there a physical connection between, let's say, KPZ equation or heat equation and random matrix theory? Is there something physical behind it?
I mean, it's, okay, yes and no. So at the level of formula, you can take the formula, interpret it in as some sort of Coulomb guess or random matrix system. And actually, there's some of the derivation I showed you earlier was obtained that way. And actually, some other work that goes as far as reinterpreting that formula as some sort of positive temperature. Okay, okay, I can't remember that. So if GUE can be thought of as zero temperature simple harmonic quantum system of simple harmonic oscillator, and you can cook up a positive temperature version of this, and that some observable of that system match exactly some observable of KPZ equation. So in that sense, there's the exact mapping. But the physics mechanism behind this mapping is not clear. And as far as we can tell, it's only matching of formulas.
Yeah. Yes, thank you very much.
There was a question in the chat.
There's another question here, yes.
So it asks, did I explore the case when the noise is fractional? I did not. So, so there are several different angles which you can sort of explore. Most of the thing that I discussed here, except for the last result, is relying on the exact solvability. As far as I know, I don't know if there's any exact solvability in the fractional noise case, but no one says that that's the only approach. So there's other things that I did not mention. For example, this physics work here. You know, essentially what they do is the friendly vessel large deviations. That's holding true for a short time. But anyways, friendly vessel large deviation. So in principle, that thing can be done. So if for a setting where you don't have exact solvability, there's still some other large deviations which you can employ. And I'm not currently exploring it, but it's something that can be done.
I have a question.
Yes, please.
So in dimension one, what's the reason that somehow people are able to manipulate the moments to compute the Laplace transform and get a distribution? And is it, how likely do you think something like this can be done for dimension two?
Okay, so you asked the wrong person for that question. So I said this is the way I describe it is completely understandable. And in itself, this is I mean, this is just surely wonderful, literature that we have. If you look into how people manage this, the only way I can say it, it's just a wonder in itself. I have no intuition whatsoever how it's being done. I can follow the math, but I can't really I don't have the kind of mentality to carry out those calculations. So to me, it's something great has been done. I'm not an expert in that regard. Now, can that be done in two dimensions? My guess is no. But there's something that one could try to explore. So in the case of second moment, the chaos expansion looks particularly simple, regardless of the dimension. In second moment, it's just a single string of diagrams. Mm-hmm. And on the one hand, we have that diagram, regardless of the dimension, 1 or 2. On the other hand, in one space dimension, we have this nice formula which specializes into the second moment case. And one can try to compare them. It actually has been done. I can't remember where the literature now, but it has actually been done. So, you just try to compare how these two kind of formula of very different nature are being matched to each other. And you try to upgrade into 2 space dimension. I don't see a way to do it, but that's, I think, a reasonable place to start.
Because in dimension 1, there's a big difference between the chaos expansion in dimension 1 versus dimension 2. Thinking, if you look at the second moment, in dimension 1, you just have a sort of finite order chaos. The finite order chaos give the dominant contribution.
Right, but I'm guessing I'm thinking in more sort of algebraic terms. The analytic behavior are totally different. I agree with you, but I'm thinking more in terms of algebraic terms. If the formula, can you match your formula, and if they match, can you upgrade those kind of matching to 2 dimensions? And there's a big difference in there too. It comes out of some calculation, and somehow that works in one dimension. It doesn't seem to work in 2 dimensions. That's what I recall.
Okay. Yeah. Thank you. Thanks for the talk.
Sorry, so there's a question in the chat, an academic question. Which software do you use for showing the PDF and making the notes? What is it called? It's Draw. Actually, if you look to the top left, I'm not sure if you can see. It's called Drawball PDF. Drawball. PDF. All right, hope I answered your question.
So if there are no further questions, so let me thank the speaker again for a very nice talk. Congratulations once again to the prize. It's very well deserved. Well, we all hope to see more papers on this topic from you. It's very exciting.
Thank you.